Modeling with differential equations. Okay, so we've got a question on page 326 and it's question and it's example 27, and basically it says the rate of increase of a population P of microorganisms at time t in hours, so always write that down, t, okay, is given by, and we've got a differential equation which is the rate of change of population per unit time equals 3p, where k is greater than 0. And it says initially the population was of size 8. And then it says, so basically initially the population size was 8, so we write PO equals 8. Find a model for P in the form, so I've got to find P equals AE3T, stating the value of A. Okay. T equals 3p, and I'm going to solve this differential equation by separation of variables because that's the only method you have learnt. So we are going to have 1 over p dp equals 3 dt. Integrate both sides. 1 over p integrates to ln p equals 3 is going to integrate to 3t plus ln c. And the reason why I'm using ln c as my constant is because it will make my life much easier once I try to put it in this form. Okay, p equals AE3t. So next thing I need to do is that I've got, basically if I want to find p, I'm going to have to take e to the power on this side. So get rid of ln by doing e to the ln p, so that's going to give me p equals e 3t plus ln c. And what that does is, that is the same as p equals e3t times e ln c. That gives me p equals e3t times c, because e and ln cancel themselves out. And now I have got p equals c e3t. This c is a constant. Okay, so now I'm going to use my boundary or my initial conditions here. At t is 0, p is 8. So I'm going to use that fact. At t is 0, p equals 8. So 8 equals c e0. And that gives me c equals 8. So that means p equals 8e3t. And that was the value of a that they wanted in part A. Okay, so a equals 8. Part B says, find the nearest 100 the size of the population at time t. So at time t equals 2, I've got to find the population. So that's just going to be p equals, if p is equal to 8e3t, then p equals 8e3 times 2. That gives me p equals 8e6. And if I plug that into my calculator, that will give me 3227.4, which is, to the nearest 100, 3200. Okay? Part C says, find the time at which the population will be 1,000 times its starting value. So, starting value was 8. 1,000 times will be 8,000. And I've got to find the time at which that happens, which means I am now trying to solve this equation. Okay, so I want to find what t is. So I want to bring it to this side. E3t will be 1,000. Then 3t equals ln 1000, and that gives me T equals 1 over 3 ln 1000, and that gives me T equals 2.3 hours, which is 2 hours and 18 minutes. Okay. Part D says state one limitation of this model for large values of t. So let's look at my model. I've got p equals 8e3t, and as t tends to infinity, p will also tend to infinity, and that's actually not realistic, okay, because the population could not increase in size in this way forever, because our limitation will be food, space, and also how the population interacts with each other. So that is actually not sustainable. So I'm going to write the population could not increase in size in this way forever due to limitations such as food or space. Okay, example number 2 is on page 327, and it says it's got a container. So let me quickly sketch that. Got some mortar in it. That's the height of it, and we've also got the diameter of it, which is 20 meters. So the question says, water in a manufacturing plant is held in a large cylindrical tank of diameter 20 meters. Water flows out of the bottom of the tank through tap at a rate proportional to the cube root of the volume. So let's just start by writing a few things that we know. So we're talking about a cylinder, we're talking about water inside it, so that's going to have something to do with the volume. So let's write down the formula for volume. And it says water flows out at the bottom of the tank through a tap at a rate proportional to the cube root of the volume. So that means dV by dt is equal to minus, because it's flowing out, some constant, which we don't know what it is, to the cube root of the volume. So that's going to be cube root of V. Show that t minutes after the tap is opened, dH by dt is equal to minus k h cube root for some constant k. Okay, so let's just work out the volume of this cylinder. So volume equals pi times 10, because our radius is going to be 10 squared h. That's going to give me 100 pi h. So that is our volume. So that means dV by dH is equal to, so if this is the volume of the tank, then if I differentiate this, I'm going to get 100 pi. That's dV by dH. We also know dV by dt, because they tell us that in the question. The reason why I've got a C in front here is because it said dV by dt is proportional to the cube root of volume. And then when I make this an equation, I'm always going to have a constant. So dV by dt is minus C cube root of V. And what am I trying to find? So I'm trying to find dH by dt. So dH by dt is going to be dH by dV times dV by dt. And that is going to be, so dH by dV is just the reciprocal of this, which is 1 over 100 pi, times by dV by dt, which is minus C root V. and I need to substitute the value for v in here, and our v is 100 by h, so 100 by h cube root. Now this is going to give me minus c cubed 100 pi, and I'm going to take this out, over 100 pi. And what's going to happen is that all of this is actually a constant. Okay, and that's what they're asking us to show, that dh by dt is minus some constant cube root of h, and actually we've shown that. So this is minus k cube root of h, okay, where k is all of this. So I'm going to write that explicitly. K is equal to c cube root of 100 pi over 100 pi. Okay. Next it says show that the general solution to this differential equation may be written as h equals p minus qt 3 over 2, where p and q are constants. Okay, so what I need to do here is I have got, let's write down what my dh by dt was. So dh by dt was minus k h cube root, and I now need to find an expression for h. So I'm going to have 1 over h. I'm going to bring this down. dh equals minus k dt, and I'm going to integrate both sides, so rewrite this as h minus a third, and take minus k out, and then I've just got 1 dt. When I integrate this, I'm going to get h 2 by 3 times by 3 over 2, add a 1, divide by the new power, equals minus kt plus, and I'm also going to have a constant. Okay, and then if I try and make h subject of the formula, I'm going to get 2 minus 2 kt plus 2c, and that's minus 2 over 3 kt plus 2 over 3c. And then if I want to make h subject of the formula, then that's going to be minus 2 over 3 kt plus 2 over 3c, all to the power the reverse of that, which is this. Okay, and that's exactly what they're asking us for. So our p is minus 2 over 3k actually this is our q, and our p is 2 over 3c. Okay, so we have h equals p minus qt 3 over 2, and we've shown that. Okay, in part C it says initially the height of the water is 27 meters, so at t is 0, h is 27. T minutes later the height is 8 meters, so after 10 minutes the height is 8 meters. Okay, so when t is 0, h is 27, and I'm going to plug that in. Because my p is so I've got p minus qt 3 over 2, and 27 equals p to the power 3 over 2. That gives me p is equal to 9 if I was to solve this. And then the other condition is that when t is 10, h is 8. So 8 equals 9 minus 10 q 3 over 2. Now I've got to find q. If I solve this equation, I will get q equals a half. And part D is just where you are going to substitute. So you've got h equals 9 minus half t 3 over 2, and it says find the time when the height is 1. So if you put 1 equals 9 minus half t to the power 3 over 2, you'll get t is equal to 16 minutes.